More often than not, matrices are not square. We will have matrices that represent the data that we have, which will inevitably have more rows than columns. Or we will have matrices that will represent functions that take from a higher dimensional space to lower dimensional space, or vice versa. So in this video, I will um, talk about narrow and wide matrices, how what they are all about, like what's happening with narrow and wide matrices. And here we start with narrow first. So narrow matrices, the other name for this is tall matrices. When you look at the AX equals B equation, it looks like this. But I'm going to start first picturing what's going on in when we have a tall matrix. So we have a tall matrix, all right. We have more rows than columns. It's thin and tall, narrow, and there's X and B. So like by the linear algebra perspective, when the AX equals B multiplication is happening, of course, X is a vector. In order for X to sit next to A and for the matrix vector multiplication to happen, we know that X has to have um, the same number of rows as many as the columns of A. So X have to be something like this, such that it goes, and we take it, remember the L shape that we were drawing previously? This blue um, vector is going to go and get inner producted with every single row of the matrix A. Therefore, since the columns are thin, by perspective, we will have as many rows in the X, the blue vector, as many columns of A, and we will calculate inner product with each and every one of the rows. So therefore, we will have an output B as many rows as A. When we look at a lower dimensional input and a higher dimensional um, output, it is not always intuitive to see that A is a narrow matrix or a tall matrix. But what's going on with a tall matrix? Now we see that we discussed A x equals B can be deemed as a set of equations. So if that's the case, we are talking about a set of equations in the rows of A, like when we calculate for each and every row, a11 times x1 plus a12 times x2 plus a13 times x3, yada, 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 all the way to b1. So we have as many equations as the number of rows A has. So therefore, we have more equations than unknowns. So this might look it's amazing. We have what else we would want, right? So we want equations. We want many equations to solve for the unknowns that we have. But typically, it's not always the case. It's not, so one might think someone who does not have the intuition or background of statistical modeling, one might think that many of these equations, if they are more than the number of unknowns, they are redundant. Um, and which can be the case, but more often than not, it is not. In conventional machine learning, um, we will want to have more equations, more data samples than the number of unknowns that we are trying to solve for. Such systems are called over-determined. So this is in the conventional machine learning systems. I would like to exemplify this um, with a historical example. So in your screen, you see Dr. Ohm. For those who have taken you don't need to come from electrical engineering background. Any high school physics show the relationship between a voltage and the current that's running between some element that's conductive, right? So Dr. Ohm was doing an experiment. He was collecting data, and he was trying to um, understand nature, understand the relationship between the voltage and the current. And then he changed some things. He changed the resistance. Then he had not named it as such. And then he applied voltage, and then he measured the current that goes through. And he was able to locate for every voltage the current for increasing levels of voltages, current also increase. If you eyeball this graph of this data points of voltages versus currents, you can see that oh, there's a positive relationship, and Dr. Ohm knew that this was a linear relationship, meaning I can get the voltage from sorry, voltage from the current or current from the voltage if I could understand this relationship, and this current should be coming from a voltage via a linear relationship, meaning I can actually draw a line that describes the relationship between voltage and current. This is a very simplistic linear equation. I is something AB plus B. We know that we know today, after centuries later, we know the relationship between voltage and current. The relationship is V equals IR, or I equals V over R being the resistance. And this is indeed a linear relationship. So, okay, let's try to solve for this A and B values. Notice how I'm using the word solve for. In machine learning, we are no longer going to use solve for. In linear algebra, we say solve for the unknowns A and B with the data that we acquire. In machine learning, we use the word fit to find the A and B that describes the data the best. So we have two observables, I and V, the current and the voltage, and we have two unknowns, A and B. So if I have two unknowns, one can ask with two unknowns, how many measurements should Dr. Ohm should make to correctly identify the phenomenon? Meaning, identifying the phenomenon means finding A and B, finding the two unknowns. And you can think that it can be actually two um, since in linear algebra, in algebra, we have established so far that, well, if you have two unknowns, you should have two equations, and two equations will have two lines, and these two lines are going to intersect. Easy peasy, I can find. But now, when you look at the problem of solving for equations, from the finding the unknowns that describe your data, that explain the nature of things perspective, you see that you need more than two. Why? Because if you let's say you're getting only these two data points here, the line that's going to be there, that's going to pass through these two data points, are going to be some slope that has nothing to do with what we see with our eyes, right? So obviously something's going on with these two data points, which we call noise, and therefore we would like not to be affected so badly with the presence of noise. Therefore, we collect many data points, right? So we collect I1, V1, I2, V2, I3, V3, and many of them. How many? N number of them. In, Vn. And since we know that all of them are coming from the nature, the system does not change, the nature of things doesn't change, and we get um, this set of equations, and A and B should explain them all at the same time. So let's go ahead and try to write this set of equations into our matrices. So if we have two unknowns, A and B, and that's our x, right? So we're talking about ax equals b kind of form. And now the unknowns that I have is A and B. Now I'm going to put it somewhere in this x, and my knowns, the things that I've acquired, should be here such that I get this ax equals b kind of form and solve for A and B. So if I were to collect only 2 points, I would place them like this in this matrix. And if this looks a little bit scary to you, notice that it's not scary at all. I'm taking my eggs and I'm calculating this inner product with each and every one of the rows. So if I calculate A times B1 plus 1 times B, AV1 plus B equals I1. And similarly, AV2 plus B is I2. So I am I I end up getting my desired um, matrix. But as we mentioned, if we were so unlucky to get to only two that goes through these two guys, then yes, we will be able to find the A and B by taking the inverse of this and multiplying it with I1 and I2. That would be all right. But the A and B that I'm going to find are not going to describe what I have in mind. So therefore, we understand, like as long as we're convinced that we should be dealing with a thin matrix that looks like this instead, uh, where the rows are going to keep all of my measurements, and just so that I can solve for these two elements, I think this video has reached its goal. The whole motivation of this video is to give you the necessity for um, collecting thin matrices and how they are going to be useful to find such A and B that it finds this line that goes through. Of course, I wasn't able to draw the line perfectly. It goes through this. How do we solve for A and B when we notice how I'm using again the word, the term solve for, um, because I have not yet introduced fitting. How do we solve for A and B given this set of equations? Well, that's coming soon, and that's going to be one of the next videos. For those of you who already know how this is solved, the name of this video is going to be least squares. When the matrices are wide, however, we we obviously see that there are more unknowns. Why? Because we're looking at an ax equals b like this, and in order for this multiplication to take place, our x has to be very big. X is almost always the unknown, and x has its own components, elements, x1 all the way to xm. I'm going to call m because uh, a can be defined as n by m, and therefore we will have a very small b, as small as the number of rows a has. So we're talking about more unknowns than equations, right? So this looks like we won't be able to solve anything if we get fixated on the topic of solving for. We, of course, we will have more number of unknowns than the equations. Here, just like in the previous example of Dr. Ohm, I would like you to see the number of equations are number of data points that we have, and number of unknowns are just like Dr. Ohm's V equals IR problem, where he found A to be 1 over R and B to be 0. And so the unknowns here in this situation are the parameters that describe the nature, which is the thing that we solve for to find in training neural networks or training machine learning problems, right? So instantaneously we see this problem will have infinite solutions. Why? Because we don't have enough number of equations to solve for. One example for this is a very simplistic example is, say we are given only one equation, right? And this equation is ax plus b equals y, and you're trying to solve for x. You cannot solve but you understand that your solution is a line uh, in the XY plane, right? So that's a line here in this situation. There's a little asterisk on the infinite solutions. Of course, uh, the um, the number of rows, the equations, and the little green B outputs might be inconsistent, just like we presented in the singular matrices. So we can have um, some repeating patterns of rows of A, and the rows of B can be inconsistent with what the AX equation provides. So there of course there's room for no solutions, right? And we call such systems underdetermined. And you will be surprised. This is a new thing actually. Maybe over the so if we call machine learning's history, there are several winters, of course. Yeah, but like if we call the consistent run to start in 80s, of course they start in 50s, but um, so like if we call machine learning history to be a 40-year run, the deep learning, the most recent deep learning models that use over parameterized uh, setup that has more unknowns, more parameters to fit, uh, is a new thing. So it's I can call it a 4 or 5 year thing starting around like 2021 or so, maybe 2020. The With respect to the year of recording this video, of course. The 4 year figure or 5 year figure can change, of course. So I can call this underdetermined or over parameterized regime to be modern deep learning regime. Eventually, we're trying to find one set of parameters that is going to solve for this problem, and hopefully, this is going to be well generalized. But this is too difficult to summarize at this stage in a linear algebra course. This is a whole another topic. Plus, modern deep learning models are not linear uh, models, right? They're highly nonlinear, but the over parameterized or underdetermined setup that you see here um, fits there. So I'd like to give you one example of such a wide matrix. So look at this matrix AX equals B. Our X is three-dimensional. Of course, the unknown is a point on this three-dimensional space that you see on the right-hand side. And I'm interested in finding the X, Y, Z, and I am given two equations to make it. And these two equations make, if you take the inner product with the first row, you get x plus y plus z equals -1, equivalent to x plus y plus z plus 1 equals 0. And the second one, I have only two, x minus y plus minus z equals 0, right? So um, actually this gives us a solution. Like we just don't finish that, oh yeah, there's no solution. We have a solution. So each and every one of these equations in a three-dimensional space presents a plane, right? So we are talking about actually two planes. One plane is this one, and this is the second plane. And there's an intersection of these two planes. So the intersection of these two planes which forms a line, uh, is the solution space of this set of equations. Before I generated this, like we have always learned this. So like if you're dealing with a three-dimensional space, and if you're given one equation in a three-dimensional space, it gives you a plane um, within that space, right? And like we have two planes, and if you have two planes, the solution space that you will have intersection of two planes is a line. So it is difficult to visualize, imagine, but I created this animation such that it actually expresses two equations. each equation again, two planes in a three-dimensional space forms a line. So it's hopefully it makes it simpler. But before I finish, of course I presented this of just so that you have an intuition. When you have fewer number of equations than the number of unknowns, what do you do? What do you have? How do you have infinite solutions? Well, every solution on that yellow line is a solution that accounts for this equation ax equals b, or this matrix and x, y, z, and b. But before I finish, I would like to mention uh, three-dimensional spaces are the maximum that we can comprehend because we live on a three-dimensional space. When I play this video with rotating planes on a three-dimensional space, of course we can imagine pages, like one page on a three-dimensional world. And in this world, the pages or the planes can intersect, and of course the intersection is going to be a line. That's understandable. So we start with three dimensions, and each equation uh, actually limits the solution space to a lower dimensional than the whole ambiguity, the whole madness, nothing, knowing nothing. So I reduce it to n minus one dimensional space, which is a plane in this setup, and another reduces to another n minus one dimensional space. And if you have enough number of them, if they are consistent, if I were to have a third plane, their intersection is going to, like by eliminating n minus 1, n minus 1, n minus 1, I was going to end up with 1 point. But now I ended up with a line. My last words are, this is the maximum that we can comprehend in a physical space, because this example was a physical example for us to understand what's going on. However, linear algebra deals with significantly higher dimensional spaces. So we will talk about matrices that hold 1000 dimensional um, spaces. And we will have equations that are, I don't know, 768 equations out of 1024 dimensions. And we will know, we will then talk about from these spaces, we will talk about subspaces within the higher dimensional spaces that present something like the plane that live on the third dimensional space. But this time we will talk about a 768 dimensional subspace within a 1024 dimensional space, vector space. And we will understand how they correspond, not visually, but mathematically. That's the whole thing that linear algebra presents anyway.